In this video, I want to explore how some of the math we learned in this course is applied in the field of computer graphics. Before I dive into their applications, I want to give a brief overview of what exactly these operations are. So first, the dot product takes two vectors and returns a measure of how similar they are. So if two vectors are orthogonal, the dot product will be 0. Next, the cross product takes two vectors and finds a vector which is orthogonal to both vectors. Projection takes one vector and projects it onto another. This is extremely useful when converting from one coordinate system to another. Differentiation and differential equations describe how a function changes with respect to some quantity. For example, acceleration is the derivative of velocity with respect to time, and velocity is the derivative of position with respect to time. Integrals, for the purpose of this video, are effectively a way to sum infinitely many samples of a function over some range. Now that that's out of the way, a large portion of computer graphics is simply lines and triangles. This is because they are the two most simple shapes, but yet can build up any complex shape, or at least an approximation of it. A line can be defined by a point and a direction. Using this parameterization, where S is a known point on the line, D is the direction of the line, and T is how far along the line you can get any point on the line. A triangle is a bit harder to parameterize, and usually it isn't. Instead, we recognize that a triangle has 3 points, or vertices, and is perfectly flat. This means that the edges are vectors, and by taking the cross product of two of these vectors, we get a vector which is perpendicular to the triangle. This is the normal of the triangle. Since a triangle is perfectly flat, we know it lies in a plane. The normal of the triangle will also be the normal of the plane. A plane is fairly easy to parameterize if you know its normal and a point on the plane. Where n is the normal vector of the plane, p0 is a known point on the plane, and P is any other point on the plane. Since we know the vertices of our triangle, we know 3 points in this plane, and so any one of them can be used for P0. In addition, the normal vector of the triangle is also the normal vector of the plane, so the only unknown is P. Now that we have both a parameterization of a line and a parameterization of a plane, we can create a test to see if a line intersects a plane. This is one of the most important tests in computer graphics. First, we need to test if the line is parallel to the plane. To do this, we can simply take the dot product of the normal of the plane and the direction vector of the line and see if they're 0. If the dot product is 0, the two vectors are orthogonal, and so the line must be parallel to the plane and will never intersect the plane. It should be noted that there is an edge case here, which is if the line is inside the plane. However, in that case, its direction vector will still be orthogonal to the normal, and so in our test we won't get an intersection. Now that we know that our line definitely intersects our plane, we need to know where. We want to find a point P, which is both on the line and in the plane, so it must satisfy both parameterized equations. We can simply plug the equation of the point on a line into the equation for the plane. This leaves us with one unknown, which is T. Rearranging the equation, we can find T, and once we have T, we can plug it back into the equation for a point on a line. We now know that our line both intersects the plane and where it intersects the plane. Next, we need to test if that intersection point is in our triangle. There are a couple of ways to find if a point is in the triangle. The first is to connect the point to the 3 vertices of the triangle, which will give you 3 new triangles. Then find the angles of these triangles, and finally sum the angles nearest the point. If the sum is 180 degrees, the point is in the triangle. While this is conceptually the easiest method to understand, it isn't usually used. This is because it requires trigonometric functions, which typically are more expensive than other methods. The second method is using barycentric coordinates. This is a method to parameterize a point in a triangle relative to its 3 vertices, where u, v, and w must sum to 1. The math is a bit complicated, but effectively u, v, and w are simply the ratio of their respective triangles to the whole triangle. This gives a weighting such that the point is u times a plus v times b plus w times c. If we translate the triangle and the point such that the vertex A is at the origin, we can remove the A term. This has the effect that the vector from A to C is now just C. And similarly for B. From here we can solve for u and v. Since u and v are the ratio of their respective triangles to the whole triangle, and the area of a triangle is 1/2 the cross product of two of its vectors, we can find u and v. Since the original constraint was that u plus v plus w had to equal 1, then we know that for any point in our triangle, the sum of u and v must be less than or equal to 1. This is the test. For our point, once we find its barycentric coordinates, if u and v is greater than 1, we know that the point is not in our triangle. There are a handful of other methods, all revolving around some form of barycentric coordinates. For example, by translating the triangle and point such that P is at the origin, you get the following equations. Barycentric coordinates are often the preferred method because it's often the case that after finding the intersection point, you're going to want to find the value of some property at that point. Usually, when you have a triangle, you're going to have properties defined only at its vertices rather than over the entire surface. And so using barycentric coordinates, all we have to do is replace A, B, and C with the value of the property we're trying to find at those points, and then the barycentric parameterization will tell you the value of that property at the intersection point. In computer graphics, the primary usage of vector projection is in shaders, which are programs which try to recreate visuals by stimulating light. In high school, we learned that if light hits a mirror, it will be reflected such that the angle of incidence is equal to the angle of reflection. But in 3D, it can be hard to find these angles. So how do we find the vector after it has been reflected? If we treat light as a straight line, then we can parameterize it, where our known point on the line is simply the light source. From there, we can find its intersection point on the surface we're reflecting off of. Once we have this point, the direction of reflection is given by this equation, where v is the direction vector of our line, and n is the normal vector of our surface. This will give the direction vector of our reflected line, and the start point of that line will simply be the intersection point. The majority of this course focused on integration and differentiation over scalar and vector fields. Unfortunately, in computer graphics, integration and differentiation aren't used a whole lot. They exist in the theory, but often are impractical for the application. That being said, they're still extremely important. The job of computer graphics is often to create visuals which look real. To do this requires simulating fluids, cloth, and other materials. These simulations rely on physical descriptions of the system. These descriptions usually come from physics, which primarily uses differential equations. Perhaps the most famous integral in computer graphics is the render equation. This equation is rather complex, but states something very simple, that the light leaving a point on a surface is equal to the light being directly emitted by that surface at that point, plus all the light bouncing off the surface. In this equation, L0 is the light of wavelength lambda at time t given off by a point x in the direction W0. LE is the light of wavelength lambda being directly emitted by the point x at time t in the direction W0. Then there's this integral, which is the integral over the surface of a unit hemisphere centered at the point x. FR is the bidirectional reflectance distribution function, which is a function which returns a physical property of the light. It effectively tells you how the light is going to bounce off and scatter from the surface. For a perfect mirror, it would be 1, and for anything glossier than a perfect mirror, it'll have lower values. Li is the incoming light of wavelength lambda at time t to the position x from the direction Wi. Wi will be the negative direction of incoming light, and n is simply the normal vector for the surface. This integral is rather complicated and requires perfect knowledge of the light incoming to a point x, which is often impossible. Instead, for computer graphics, we do the reverse. For each pixel we want to render, we can make a vector entering the world through the viewport. We can then find the triangle which this vector intersects and the point of intersection. From this point, we can use the reflection equation and FR function to create several random vectors from that point. We repeat this process for these vectors, removing vectors after a specified number of collisions, and this gives a random sampling which simulates this integral in a way that's realistic enough without requiring infinite computations. A rather interesting use of the gradient operator that I found had to do with volumetric lighting. If you have a volumetric function which gives the density of something, such as clouds, then the light given by any point in that volume can be represented as this gradient, where x is the position and v is the direction of incoming light. There's also a rather famous example of Newton's method being used in computer graphics. This comes from Quake 3 Arena and was used to calculate the inverse square root of a number. Square root in general tends to be fairly computational taxing, as does division. The developers managed to use Newton's method and differentiation in order to find a much faster, yet approximate solution to their problem. Lastly, I want to look at two applications which are extremely complex, yet which integration and differentiation are defined on and frequently used. The first is surfaces designed in CAD software. These surfaces can be defined by either parameterizing the surface itself or the volume. These surfaces are frequently used when designing objects, including airplanes, where you need to test how that object is going to react or handle certain conditions. Because these surfaces are parameterized, you can take integrals over them, which allows you to do things like compute how they're going to interact in a fluid. In addition, if you know the materials being used, you can use integration on these surfaces to find out how much the object will weigh, as well as other properties. There are also Bezier curves. These are curves defined by control points so that the curve is continuous. A first-order Bezier curve has 2 control points and is a straight line. A second-order Bezier curve has 3 control points and is a quadratic curve. A third-order Bezier curve has 4 control points and is a cubic curve. While any higher-order Bezier curve is possible, usually only the first, second, and third-order Bezier curves are used. This is because as the order gets higher, so too does the computations required in order to calculate the curve. However, any complex curve that is continuous can be built up from only first, second, and third-order Bezier curves. The important thing is that these curves are continuous and have known parameterizations. This means that all the calculus we've learned in this course can be used on these curves. Oftentimes, Bezier curves and parameterized surfaces are used in order to do physical simulations, both to test properties but also in computer graphics to create more realistic visuals. At the end of the day, and under all the fancy graphics, the entire field of computer graphics is based solely on math. And while much of the math is complex, with equations like the render equation or the Navier-Stokes equation for fluid simulations, it is all based on the concepts we learned in this and previous courses.